Hello. In this video, we're going to discuss limits, which is covered in section 2.2 of our textbook. And a limit focuses on the behavior of a function near a value c. But what actually happens at the value c is completely irrelevant to limits. Limits only see what's nearby. They don't worry about what actually happens at a point. This will be especially useful later on when we return our attention to the difference quotient. That was f of x plus h minus f of x over h. And we wanted to know what happens near h equals 0. Because, of course, if you try to plug 0 into here, you get f of x minus f of x, which is automatically 0, divided by 0. And 0 over 0 is nonsense. So let's make a quick note. 0 over 0 equals I don't know. It could equal 0. It could equal 1. It could equal 3. There is no way to tell what's going to happen near 0 because 0 over 0 is completely undetermined. This is called an indeterminate form. But let's turn our attention to a more concrete example, and let's think about what happens to the function f of x given by x squared minus 4 divided by x squared plus x minus 6 near the value x equals 2. I will make a quick note to say that f of 2 is undefined. You cannot plug 2 in here. Because if you try to plug 2 into here, you're going to get 0 on the top, which is fine, but you're also going to get 0 on the bottom. And we cannot divide by 0. X equals 2 and also x equals negative 3 are not in the domain of f of x. Because if we plug in 2 or negative 3 into this guy, we're going to get division by 0, which is always against the rules. So notice that you cannot plug in 2, you cannot plug in negative 3, because this function does not make sense at those 2 points. But this function does make sense near 2. So let's draw you a quick picture.
I've used a graphing program to create such a graph. Notice that I have artificially inserted the problem at 2.
So I've drawn a graph of this function. Notice if you ask a computer or a calculator to draw this graph, it's going to draw this, and then it's going to draw this, and it's going to fill this hole in right here. Because your calculator or your computer isn't that smart. It just plays connect the dots. But we know that we cannot possibly plug 2 into here, so that's why I have a hole in the graph right here. F of 2 is not defined. There is no f of 2. I also have something crazy going on at negative 3. But we're not going to worry about that problem right now. We're going to focus on this problem. So what's happening to this graph close to 2? I don't care about actually at 2. I just care about, like, in this general neighborhood right here. What happens to this function? And we can look at function values nearby, such as if we ask what f of 2.1 is, that gives you 0.8039, rounding up decimals-ish. So with a little weighty equal sign, meaning it's close to that, not exactly. We could also do f of 2.01, and there we get 0.8004. I also tried something a little bit smaller than 2, 1.999, and my value there was 0.799996-ish. So it looks like this guy is getting close to 0.8. Close to 0.8. But this is not really math. This is not math. This is what we call kind of guess and check. This is not math. So we have to come up with a better system. We have to come up with a better way to find values, because just plugging in numbers nearby, you can come up with some really crafty, weird things where numbers nearby look like one thing, but something entirely else is going on there, just depending on what kind of numbers you choose. So this is not really mathematics. Sure, it gives me the idea that I think it's going to get close to 0.8, But this is not really mathematics. I need some actual math, so therefore we're going to employ what are called some limit laws. Well, the first step in limit laws is talking about what is a limit in the first place. So suppose that f of x is defined in an open interval around c. Not necessarily at c, but just in the general neighborhood around c. There's an open neighborhood around c. If f of x gets arbitrarily close to a value L, as x gets close to c, we will say that the limit as x approaches c of f of x equals L. So this is the mathematical notation for it. The limit of f of x as x approaches c is L. Limit of f of x. So what are you taking the limit of this as x approaches c is, that's an equal sign, L. Or you could also say f of x approaches L as x approaches c. Or you could say as x goes to c, f of x goes to L. But this pink notation, that's the notation we're going to use the most. But these are the different ways you could say that exact same thing. The idea is if this value of f of x gets arbitrarily close, we're not going to nail down mathematically what that means. But what it's saying is you tell me how close you want f of x to be to L, and I can choose an x very close to c that will make these two numbers as close together as you want. For example, if you want f of x to be within 1,000th of L, I can choose an x that's close enough to c that'll get it within 1,000th for you. So the limit of f of x as x approaches c is L, or you can say the limit as x approaches c of f of x is L, or f of x approaches L as x approaches c. All of these mean the exact same thing. So this is what we mean by a limit. But I think if we actually have some rules and some hard examples, it'll work a lot better than all this weird abstract stuff. We're going to start with two basic limit laws that make pretty good sense. The first one is the limit as x approaches c of the number 2. Well, as x gets close to 7, as x gets close to 12, as x gets close to negative 43, what's going to happen to the number 2? It's going to stay the number 2. So the limit of a constant is in fact just that constant. All right, well, sure. Basically, imagine a horizontal line. I don't care what x you're close to. The value's 2. As x gets close to c, what do you think happens to x? What's the limit of x as x gets close to c? Well, I guess it's c. What happens to x as x gets close to c? Well, apparently x gets close to c. And believe it or not, these two pedantic, simple limit laws actually build up most of it for us. So let's build from there. Suppose that the limit as x approaches c of f of x is some number L, and the limit as x approaches that same number c of g of x is m. So f of x is getting close to L, g of x is getting close to m, as x gets close to c. Well, what do you think happens to f of x plus g of x? You just add this limit to that limit. You take this guy's limit and add it to this guy's limit. Well, you add them, you add them. Well, if you subtract them, you subtract them. If you multiply them, you multiply them. If you divide them, this works as long as m does not equal 0. Division by 0 is always a problem. But as long as m doesn't equal 0, we're set. If you multiply f of x by 3, that's going to multiply the limit by 3, or any other fixed number. I just chose 3. If you raise f of x to a power, it just raises the limit to that same power. I just use the letter n as a power. And if you take the nth root, it's going to be nth root is L, and we'll just make a quick note. If n is even, L had better be at least 0. Because I cannot take the square root of a negative number. So if n is an even number, I better be taking the even root of a positive number. If n is odd, it doesn't matter. You can take the cube root of -8, that's not a problem. You cannot take the square root of -8. So you still can't divide by 0. You still can't take the square root of a negative number. But beyond that, you do what intuition tells you to do. You just add, multiply, all that fun stuff the whole way through. Let's do a couple examples with these limit laws. So the first one I like to think about is the limit as x approaches -3 of x squared minus 2x plus 8. Well, this is something minus something else plus something else. So this is really 3 separate problems. All right, so let's look at the first one. The first one is x squared. So we can take our function x and we're going to square it. So that's just going to be what happens to x as we get close to -3. That gets close to -3 and we square it. All right, so I just took the x and I squared it, okay, minus. Now if I have a constant out front, the constant just comes along for the ride. The x gets close to -3. And of course the 8 is always 8 regardless of the limit. So we get 9 plus 6 plus 8, which is 23. Bam. You'll notice that what it looks like I basically did is I just plugged in -3 here, here, and here. And hint, you should always just try, whenever you see a limit, you should always just try to plug in. Just plug in, keep your fingers crossed, and hope it all works out just fine. Of course, the interesting limits are the ones where that's not straightforward. So let's look at x. As x approaches -2 of x plus 2 over x squared minus 5x minus 6. All right, let's look at this limit. Well, this is something divided by something. That's this rule right here. So let's do the limit at the top, limit at the bottom, and see if it works out. All right, limit at the top. If I try to plug -2 into here, let's see. That's going to be -2 plus 2 is going to be 0. If I try to plug -2 in the bottom, I'm going to get 4 plus 10 minus 6. This is 0 divided by 8. 0. You can divide 0 by 8. That's not a problem. It's the dividing 8 by 0 that's a problem. 0 divided by 8, that's just 0. However, notice if the limit as x approaches 6 of, let's see, x plus 2 divided by x squared minus 5x minus 6. If we try to do this, we're going to get 8 in the top, but notice we're going to get 36 minus 30 minus 6, which is 8 divided by 0. Gross. So that we can't do. We will say this limit does not exist. And we will talk about this more in section 2.6. So our first example was 0 divided by 8. That was 0. Our next example was 8 divided by 0, which means the limit does not exist. Something has gone completely crazy. More about this in section 2.6. Third example I want to consider is x minus 6 divided by x squared minus 5x minus 6. And if I try to plug 6 into this guy, I get 0 over 0. And when you see a 0 over 0, first of all, that's not actually an answer. 0 to 0. When you see that, that means more work is needed. So if you see a 0 divided by 0, immediately think to yourself, more work is needed. And if you get, when you plug 6 in the top, you get 0 because, well, you plug x minus 6 into here. Well, what that means is that the bottom must also have a factor of x minus 6. If when you plug a number into a function, you get 0, that means that x minus that number must be a factor of this guy. So therefore, we have x minus 6. Well, if I'm going to factor this guy, I guess my only possible action is x plus 1. That's the only way that I've ever multiplied a -6. And you can check that if we FOIL this out, we get that guy right there. And now, because we are working with limits, I can cancel this term with this term. Now, if x equaled 6, I would be dividing the top by 0 and the bottom by 0. But x does not equal 6. X is just close to 6. So, therefore, I am allowed to factor this term out, cancel. There's still a 1 in the top because this is x minus 6 times 1. X plus 1 in the bottom, 1/7. So if you get a 0 divided by 0, that means more work is needed. And your hint is that if when you plug in 6, it makes it equal 0, that means that x minus 6 must be a factor. This is called the factor root theorem. If it zeroes it out, then it must be a factor. So therefore, you've already got some of the factoring done. You can factor, you can cancel, and get this. It is critically important that you write the word limit there, because this statement right here, while it looks almost true, these two things are only equal to each other if x does not equal 6. For any other number in the whole world, these two functions are the exact same thing. But if x equals 6, this is 1/7. If x equals 6, this is 0 divided by 0. So that means that this side is complete nonsense, and this side is 1/7. Therefore, these are not the same thing if x equals 6. But as long as x doesn't equal 6, these are exactly the same. But it's a good idea to just remember to write your limits there until, of course, you've taken the limit. Notice I didn't write the limit in front of the 1/7. I already took the limit. Taking the limit is a verb. It's an action. Once I've done it, I'm going to stop telling myself to do it. I've already done it. Why tell myself to keep doing it? So we're going to spend a lot of time in class. I'm going to throw a couple examples at you, like this guy, the really easy one, or maybe like these kind of guys. But this is where the real work of limits is. It's this 0 over 0, looking for canceling factors and things like that. That's where most of the work is done. Before we conclude this section, I'd like to give you one more important limit law. All right, this final rule is called the sandwich theorem or the squeeze theorem. And it says, okay, suppose that f of x is stuck between g of x and h of x. So it's stuck between g of x and h of x for all x near c, except possibly at c, because we know if we're working with limits, we don't actually care about the 1 point. But, so f of x is trapped between these two guys. If g of x's limit is L and h of x's limit is L, well then, guess where f of x has to go? So imagine, for example, I've got my h curve drawn in yellow, my g curve drawn in blue, and I can do whatever I want with my f of x, but when I get close to c, notice that if yellow and blue are both going to this value right here, the value L, well, where else can f possibly go? It's stuck between these two. And since we live in Athens, I always get to refer to it as you're walking down the street with your two friends on either side. If they both go to the same bar and you're stuck between them, you're going to that same bar. So if you're stuck between these two guys and they're going to the same place, well, then you're going with them. And a great example of this guy will be the limit as x approaches 0 of x times the sine of 1 over x. And I could normally use my limit laws, but I don't know what happens to the sine of 1 over x. That guy, I have no idea what that could possibly be. So I need to figure this out somehow. And you might imagine I'm going to use this guy up here. And we'll start off with the fact that sine of 1 over x is definitely less than 1 and bigger than negative 1. That has to be true because sine of anything is between negative 1 and positive 1. I'm now going to multiply by x. Now, technically, if x is a negative number, I would have to turn all these inequalities around. So let's be careful and let's put absolute values on these x's. I can leave this guy alone because I'm making sure that I multiply by a positive number and not a negative number. And now notice, as x goes to 0, what's going to happen to this guy? He's going to get close to 0. What's going to happen to this guy? He's getting close to 0. Therefore, by the squeeze or sandwich theorem, this limit has to be 0. And I wouldn't want you to just write equals 0. I want you to show me some of the reason how you know it's 0. It's sandwiched between plus and minus 1. I multiply by x. This guy goes to 0. This guy goes to 0. Therefore, this guy has to go to 0. So there it is. Those are the rules for limits. So I'll see you in class, and we'll work through all those. You'll get lots and lots of good practice. Have a great day.